Hey everyone, in this video we're going to try and solve for the equilibrium position of this tan charge in between charges Q1 and Q2. So you can assume all of these charges are positive. Okay, the problem doesn't actually specify what the charge for the tan charge is. So we'll just call that Q3 for right now. Okay. You should notice that both x and the distance between Q1 and Q2, the distance d, both of those are measured from the leftmost charge. So let's just call that, in other words, x equals 0. All right, that's the 0 position, and the x direction increases to the right. Okay. All right, so the problem says that the charge of Q1 is 4 times greater than the charge of Q2. We can kind of see that in the relative sizes of 1 and 2. And the separation distance between 1 and 2 is 1.8 meters. Okay. So what do we do first? Well, for any of these problems that you'll encounter, my suggestion is to draw the force arrows, right, on the charge in question. In this case, it's charge 3, so let's draw the force arrow due to charge 1. Okay, if they're both positive, there'll be a repulsion force on Q3, so that would want to push it to the right. All right, and we can write that force on 3 due to 1, right, and that nomenclature is specific. Okay. Force subscript 3 due to charge 1. Okay. Now let's draw the other force arrow on 3 due to charge 2, and that's also repulsive, but it wants to push it to the left. So we'll draw that the force F on charge 3 due to charge 2, vector. Okay. For right now, I wouldn't worry about the relative magnitudes of these forces. Just draw an arrow. Okay. Now, time for some math, the fun part. So, what we need to do is find the force on charge 3, but the net force, right? So we can write that like such. And how many forces are at play? How many terms will we have? Well, there's 2 forces due to 2 charges, so 2 terms. The positive direction is to the right, defined by the problem. So that means F31 will be positive. Well, we'll see it's positive later. For right now, let's leave these as vector notation. Okay. So as vectors, they're both positive. And we're only worried about the position. Okay, we're not necessarily worried about the acceleration. Or how fast Q3 moves, right? The keyword equilibrium there says that, well, actually, it doesn't accelerate. It doesn't move. So actually, the net force should be 0. Okay, and that'll be important. All right. So what do we do now? Well, there's only one effective direction or one effective axis, and that's x. So this is a 1D problem. Let's write the first term here in terms of Coulomb's law for the force on 3 due to charge 1. Okay, so we have the Coulomb constant, we'll keep that as K for right now, times the product of the charges, Q3, Q1, divided by the distance between those charges squared, that is x, between 3 and 1. And which direction is that? That's to the right, so we can call that I hat. Right? So that's our unit vector, the magnitude unit vector in notation. I had a small brain fart there. Okay, next one. Force 3-2 points to the left, so this one will be negative. Coulomb constant times the product of those charges, Q3 and Q2, over the distance between 3 and 2. Well, if d is the distance between 1 and 2, then the leftover distance right there is d minus x. And so that distance we can put in the denominator here, d minus x quantity squared. In which direction does that point? Points in the negative I hat direction. You can keep it like this, but that's also the same as that, right? The negative I hat direction. Either one is fine. All right, and again, this equals 0, okay? So if you can foresee a couple things happening, we're adding two terms to be equal to 0, so I'm going to bring one term to the other side. Doesn't matter which is on the left. Q3, Q1 over x squared, k Q3, Q2 over d minus x quantity squared. I'll drop the unit vector notation for right now because we know they're both in this I hat direction or this x-axis, okay? All right, so now constants cancel out on both sides. K goes away, and the unknown amount of Q3, which is good because the problem itself never specified a charge, right? That's another clue in these problems that you might not need that value if the problem doesn't state it, okay? And so now, what are we trying to solve for ultimately? Well, we want to solve for x, right? The unknown value x in terms of the given distance d, okay? And now it's just a matter of cross-multiplying and solving for x. So let's see, what am I going to do? I'm going to keep the charges on the left side, right? So divide both sides by Q2, bring the x squared to the right, gives us this, and realizing that Q1 over Q2 we can actually get a value for, right? Remembering that Q1 is 4 times Q2, I'll write that over here. 4 Q2 divided by Q2, right? Also, the problem never stated the value for Q2, so those go away. And now we can actually square both sides of this equation, which is handy. So that gives us, I did it again, x over, well, I guess I don't need parentheses now, d minus x equals 2, right? And then now, taking the d minus x to the right side, I'm going to run out of room very quickly. We have x equals 2 times d minus x, which equals 2d minus 2x. Take the 2x to the left side. Oh boy, running out of room. We have 3x equals 2d now, and solving for x gives us 2/3 the value of d, which should equal 1.2 meters. So now that we have a final value for our problem, it's worthwhile to see if that actually makes sense, right? 1.2 meters as measured from the left side, as measured from Q1. Well, is that, say, halfway, or is it greater than halfway? Halfway would be just about here, and halfway would have a value of half of 1.8, which would be 0.9 meters. So 1.2 is indeed to the right of 0.9. That makes sense because the charge of Q1 is greater than Q2, thus the electrostatic force that we drew here to the right will be greater than the electrostatic force we drew going to the left. And so thus, that would push this tan charge further to the right, closer to charge 2. So yes, our value of 1.2 meters does make sense. And in fact, that's the answer.